So in this presentation we'll look at some code forensics, and we'll start off by looking at some computer architecture to see where systems are actually going and to identify what type of code that machines understand. Then we'll look specifically at Microsoft.NET and the type of code that it produces, and we'll look at an example of the obfuscation process where we should find out that .NET and Java are fairly insecure in terms of reverse engineering, so we need to use techniques such as obfuscation to overcome that. Then we'll quickly look at some behavior analysis, some network analysis, and then we'll finish off with some practical .NET host-based forensics systems. Okay, so what's the focus of this presentation? Well, we'll have a look at some static code analysis. Then we'll look to see the methods that someone might use to be able to regenerate code or reverse engineer from our machine code back into source code. We might also use the same techniques in terms of a code review or debug, where we find bugs, we validate and evaluate programs. We might also look at some sort of damage analysis. If we have a piece of malware, how we can actually analyze what damage it's actually done to the system. And then finally, we might use it to be able to identify the basic network or host behavior of an executable program, such as the CPU utilization, memory, the network connections it creates, the communication protocol it uses, and so on. And we might also look at the payload analysis for the code execution, so that we can actually detect any piece of malware coming through our systems. So why would we use code forensics? So there are possibly many reasons that we can do this. We can obviously recover code from an exe. We might look at code metrics to be able to evaluate how something actually runs, and obviously its basic footprint. What's the memory utilization, what network connections to use, and so on. And we might also analyze our code to be able to see if there is any data leakage or even spyware actually on our programs. Again, we might look at some vulnerability analysis. What's the stress points inside our program? Could look at code optimization to understand the bottlenecks by running the executable through some sort of debugger. We might use it for some sort of reverse engineering, or someone might use it for that. There could be a legal challenge to analyze a program to see where liability lies for any damage. We might use it for debugging programs for bugs and in terms of damage analysis. So really we split into two main sections when it comes to code. In terms of humans, we mainly understand high-level languages because they're fairly easy for us to read and interpret. They're written in a pseudo-English form, in an algorithmic form. They tend to be fairly mathematical in their approach, so we can easily represent mathematical techniques and logic. So two examples of this are C++ and C#. We can see here that it's fairly easy for a human to read these languages. Unfortunately, computers don't understand this type of program directly, and all they really understand is machine codes or binary code. So the types of code that they understand are similar in their abstraction to this type of code. So we see here Intel 86 code, ARM code, and intermediate code. This type of code is near the actual machine code that a computer would actually understand. We can see that it's still in a form that is readable by a human, but these would be converted into opcodes and obviously into binary for a computer to actually understand. So we'd call languages here high-level languages, and we call languages here low-level languages. But basically all our high-level language becomes some sort of machine code at some time because it needs to run on a processor. So the basic flows that we have is that we can either have a compiled language on this side, and with a compiled language we have languages such as C++, Fortran, VB.NET, Delphi, C#, and so on. They go through a compiler which checks the syntax and does other validation tests. Some will even check for runtime errors. From here we get our object code, and then from our object code we communicate with a linker which brings together lots of different object code files, and also with static libraries that might have things like the code to write to the screen or read from the keyboard and so on. This object code can't exist as a program on its own, as it doesn't have the fundamental building blocks that come from other OBJs and other bits of code. So the link is thus required to create an executable code. So the output, if everything is okay, is an executable or runnable code, which is the machine code to be able to run on the computer. This, when it's run, creates normally a process, and the process itself doesn't have to have all the code that's required to run the program. At one time we compiled very large programs and ended up with very large EXEs. These days we can port the executable alongside DLLs or with standard DLLs, so that when they run they call the DLLs as required. So if a program wants to use the USB adapter, it might call the code that's required from a DLL which holds the USB code. Once it executes it and it doesn't need it anymore, then it can put it back, and it doesn't actually need to keep running the DLL. So we have a whole lot of other DLLs that we might use in our process. So this type of code is fairly fast. It's optimized for the architecture that we're running the system on, and it's also fairly good at checking for errors either before runtime, such as syntax errors, or within runtime. Especially languages such as VB.NET and C# are very good at spotting errors that could occur while the program is actually running and try to catch them. So the other type of code that we get is the interpreted code. So this includes languages such as BASIC, Lisp, Python, Ruby, ASP, PHP, JavaScript, Tcl, and so on. These tend not to be these are not compiled, so the system must interpret the code as it's actually running. So for example, JavaScript, a web browser, reads the JavaScript and actually runs the code inside the browser on the client. This is then, the interpreter then converts it into runnable code. This type of language, the interpreter, is much slower than compiled, as it's non-optimized and must be interpreted. It can also be error prone, that it's fairly easy for an error to happen and then at runtime for the error to go unchecked. So this type of code is often preferable. It's easier to create more compatible code here because we actually know the system that we're writing for. Over here we can have problems with the version of the code. And this often happened with JavaScript, that it mattered what browser was actually running the JavaScript, as JavaScript was in the past continually changing. Okay, so let's look at the architecture that we design our code for. So this is highly important as it provides the key as to what type of code that we see at machine level. The three main types of architectures used at the present time are the standard Intel x86 code, the 32-bit architecture. We're now seeing 64-bit code, especially in Windows 7 64-bit, but increasingly we see this ARM architecture, which is used in mobile phone type technology. Low-powered type processor, and is now becoming extremely popular. So the three main types, main classifications that we have. So we have the standard x86 architecture, which has grown up through the 886, 888, 8386, 8486 onto Pentium, and now on to the Intel I series. Along with this, we get different ranges of processors, such as the Intel Atom, which is often used in netbooks because of its low power and fairly good CPU throughput. We also get fairly general processors that are fairly powerful and are used in notebooks. So with x86 we have a 32-bit data bus, and it's been used in DOS, Windows, Linux, BSD, Solaris and Mac OS. The basic architecture of an Apple Mac or a MacBook is around the x86 architecture. The newer type processors are the 64-bit ones, and though these support a 64-bit data bus, and that includes the i7, Intel Xeon and so on, and that's supported in Windows 7, Linux and Mac OS. An increasing amount of devices actually use the ARM architecture. So ARM licensed the technology to chip manufacturers such as Samsung, who produce the chips, and then they are used in a wide range of devices. So we're now seeing it in Android, Chrome OS, Fedora, Ubuntu and many more. It's used within Apple iOS, such as in the iPhone and the iPad, and it's likely that the next release of Windows, Windows 8, will support the ARM architecture. So if we look at the range of devices that we typically will compile to, at the bottom end we see the mobile processors, such as the ARM ones. So a typical one is the ARM Cortex A8. It's about 600 MHz CPU, has one core, and we'll see how cache memory, etc. Is used in future slides, but it's a fairly small amount of level 1 cache. Very low power. When you see that up at the higher end, we're looking at 165 watts for the processor. The A8 is only around 0.3 watts, and it's used within the iPhone 3GS device. The architecture that's just been rolled out is the ARM A15 Cortex. This uses dual or quad cores, so we can have 2 or 4 processors inside the mobile device, and a larger level 2 cache, and it's going to be used and is used extensively in Android type devices and future mobile phones. As we move up, we go through the Atom. So the Atom of fairly low power here, 13 watts, and fairly good speeds with 1 or 2 cores. Then up through the i3. As we can see, we're increasing the speed, increasing the number of cores, increasing the level 1, level 2 cache, and we increase the power rating. Obviously for a desktop this isn't too important, but for a mobile device it's highly important. Then up through the i5, and we start to see a throughput of 2.5 tera transactions per second, and the clock speed is increasing too with dual core. Then up to the i7, and with the i7 we see massive throughputs of 6.4 gigatransactions. That's 6.4 billion transactions per second, and we have between 4 and 6 cores with a fairly fast speed. And then the device that's typically used in server type technologies, the Intel Xeon, where we can have between 1 and 8 cores, lots of cache memory and a very high throughput. So this shows us the range, and basically if we segment it here and about here, then we see mobile devices here, we see notebooks and desktop type technology here, especially towards this, notebooks more towards this end, and up the top we see server type infrastructures for the Intel Xeon. What we're likely to see is we're likely to see an increase in this market as this pushes this much more, and so that the power of the desktop is likely to increase, but we'll see many more devices in this range taking over a larger share of the market. So the simplest architecture that we can have is that we have a microprocessor. It has an address bus to be able to address the memory. Each memory location has 8 bits or 1 byte. Each byte has a specific memory location. We point to the memory location and we read a certain number of bits onto the data bus, or we write to memory. So the processor itself is defined either as a 32-bit processor if it has 32 data bits, or 64 if it has 64. Obviously, the more data bits that it has, the faster it can actually read and write from memory if it has a lot of memory to read, if the program is set up for 64 bits. So we can either have 1 core, such as in the Pentium. We can have 2 cores inside the processor, so we have 2 processors really inside the single unit. We can have a quad core, such as in the i5, where we have 4 processors. So we can run programs really in parallel. If they allow us to run in parallel, we could be running one program here, another one over here, some bits of code on this one, and another system program running on this one. So obviously the more cores we have, it's likely the faster the machine will work. We can have a hexa core with 6 cores on it, and then we can have an octa core such as the Xeon with 8 CPUs. So if we look at a very simple architecture of a computer, the processor over here with its address bus and its data bus, in this case it has 64 bits and some controls such as read and write lines. Then we have our basic memory hub, very fast chip here, which will allow the fast flow of information in and out of the chip. And over here we have our north bridge, and down here we have a south bridge. So graphics are need very fast transfers of information. Our memory here also needs very fast, and down here in the south bridge this is actually quite slow. So it's really up to this memory hub to really try and optimize the speed between the processor and the memory, processor and the north bridge, and they should take priority over the other bridge. So when we're communicating with graphics, then the data will go out onto the graphics bus through the memory hub, or if it goes to memory, then it goes right through there into the RAM and so on. Every time we go out onto this, then we slow the system down. So if we think this is about 3 gigahertz here, clock speed within the processor, we then go out onto the front end bus, which might only be about 600 megahertz. So automatically, whenever we come out from here, then we're going to slow down on to there. So as much as possible, we want to keep things inside the processor. If we go out here, then we slow things down completely because we've got the mouse and the keyboard, PCI bus, USB, and so on. Okay, so this tends to be a very slow interface. because the speeds are so high here, then we really need to make sure that all our components are actually kept cool and have heat sinks. So an important concept with inside the device is a cache. And cache is an area of memory which holds any data or code that is likely to be used within a short time. So when a processor is accessing memory, okay, so it's been accessing the memory, it is possible to predict roughly what area memory is likely to be wanted next. So if the processor has been sequentially looking through the memory one by one and reading it, then it's possible to load in a whole chunk of memory into the cache, so that rather than going out and accessing it directly, it can get access from the cache and keep very fast throughputs. The static memory is very fast memory as compared to this dynamic memory, which is fairly slow but large. So the level 1, the first level cache is here, very small amount of memory. Processor, the on-chip cache controller does a quick check as to what it thinks is likely to be hit next. By the time the processor tries to access it, then the cache controller says, I've got it in there, you can have it from there, and then it can actually access it. So the more cache that we have here, obviously the better chance that we have of getting that guess correct. We can also have a second level cache that's off the chip typically, and we have a controller board for that. This tends to be a larger area of cache, so we could be looking at 60 megabytes of memory, cache memory here, fairly large, as opposed to something like 64 gigabytes for a server here, quite a large area of memory. And this might only be about 256K. So as we can see, our areas of memory are typically seen on the chip, so that looks like a large area of memory on the device, and that's likely to be the first level cache memory. If we look at the i7 core, so we can see here there's the 4 cores. There's 4 cores on it there. This is likely to be an area of the cache memory local to the core. We can have a level 2 cache, and we can see here that it even has a level 3 shared cache area between all the processors, and it's quite a large area of cache. Over here we've got sort of memory control that we see, these type of elements. And then we've even got a graphics processor actually on the chip. Unfortunately, if we get a miss, then the processor itself would have to go straight out to the dynamic memory. But as it's loading through, then it recalculates and refills up the cache, so hopefully it doesn't get it wrong the next time. So if we look at a typical motherboard, we can see here's the processor. This is likely to be the north bridge because we can see that this is it's got a heat sink and allow it to be likely to be very fast throughputs. We have our main DRAM memory here. This is our IDE, our floppy disk controller. We have power socket here. This is the PCIe and our PCI adapters. And so on. So in this part we'll look at some code types because they're not all the same as in there tends to be some kind of, there could be some interface between the actual running of the code and the hardware itself. Either it could run directly on the hardware, or there is some intermediate agent which is converting from native code into the actual machine code of the architecture that's running. So the first basic type that we have, and this is the most traditional form, is that we have our program which is compiled into our machine code or our OBJ file specifically for the architecture that we're looking at. That then produces the exe which runs directly on the hardware. The advantage with this is that it's fairly fast because it's optimized for the hardware, and it can be difficult to actually reverse engineer the executable back into the code again. The problems with it though is that it's very hardware specific, so we typically can't run it on other types of architecture. It's unmanaged code where the code runs directly on the hardware and can obviously do damage to the hardware or to other pieces of code running on the system. It's also difficult to debug as the link between the code and the actual machine code is often lost unless we leave on debug with inside the compilation. The link between the code, the machine code and the high-level code is often broken. A major advance happened when the code was seen to be run with inside a managed environment, such as for .NET with C# or VB.NET. With this, we compile to an intermediate code, which is an abstraction of how the program should run on any type of machine. That is then read by the .NET runtime. It's fairly efficient, so it doesn't really have to be interpreted. It's run in real time and then is then converted into the code that's required to run on the hardware. So this shows an example of the Microsoft Intermediate Language, or MSIL. So our C# code is converted into this format, which is then run in the .NET runtime environment, which runs on the hardware. So it's managed code, so any bad code can be managed. Code is also isolated from other parts of the system. We can make it compatible with any type of hardware, so all we need is to get the runtime on the device, so it could run on a mobile device or different types of architecture. It's language independent. It doesn't matter which language we use here. We can always produce this in some sort of format, so we can use Fortran, Delphi, Java and so on. It's fairly easy to debug as the code almost goes back into the original code in a simple operation, but it's fairly slow because it's got to run through this runtime environment, and also different versions only support certain features. And a disadvantage also is that it's actually fairly easy to reverse engineer it. Along with this, we can have Java, which compiles into a similar format, which is the bytecode. The bytecode again is an abstraction of the computer code that will then be converted into the real code on the actual device. So we can see here that the code itself is in a format that can easily be converted back into the Java code. So it's managed again, which is quite good. It's compatible with a large range of hardware. Again, it's language independent to an extent. It's isolated. It's fairly good to debug as we can get our code back. But again, with .NET, it's fairly slow. Java suffers greatly from having different versions of the runtime environment which aren't matched to the actual Java code which is running. And as we'll see, it's very easy to reverse engineer the code back. Another type of system that we have, and one that's increasing, is that what we can do is we can virtualize a whole operating system with all the programs within a virtualized infrastructure. So with this, we have our hardware. We then either fit on top of that full virtualization, such as through VMware Workstation, VMware Fusion, which runs on the Mac, and Parallels. This then allows us to run a whole host of different operating systems on a range of hardware. So we can run Juniper networks firewalls, Cisco devices, Mac OS, and so on. The other type that we have is to use a hypervisor, and this has some footprint on the system and will generally slow it down. But a hypervisor is a very lightweight program that runs and basically just enables the system to virtualize the operating systems almost directly. So good examples of this are VMware ESXi and Citrix Xen. This is often used within a cloud-based infrastructure. So the advantage with this is we can run many different types of operating systems, many types of hardware, and on many types of hardware. There's a reduced requirement for hardware, as that we can just have generalized hardware and we can run multiple operating systems on it. Doesn't matter what the native code actually is, we can still run it on code that it hasn't been built for. We can also define predefined environments. We can sandbox. Often what we can do is we can set up virtual instances which are virtualized. We can then set up a network which connects them, which is completely isolated from the rest of the internet, so that they can actually communicate together in an isolated way. The disadvantages is that it can be slow, especially in this area here, for VirtualBox, VMware, Workstation and so on. It takes up lots of memory, and it could actually breach the original license of the operating system. For example, running a Juniper firewall might actually breach the licensing terms required if it was run within a virtualized environment. And basically it will take the native, the calls from the operating system and convert it into the native operating system call. This is how it works really, and that all these devices here use the x86 architecture, which has this type of structure. Ring 0 is the most trusted level, and that runs the most highly trusted code, such as system calls. And then as we go up, all our applications run in this ring. With full virtualization, we interface into this layer here, into ring 1, and the virtual infrastructure translates this into the ring 0. For the power of virtualization, we have VMware ESXi, Xen, Citrix, KVM, and so on, and they use what's called the hypervisor, which sits between the guest operating system and the ring 0. And so this is what's called bare metal virtualization, where the operating system almost sits on the processor itself, and programs within inside it can't tell that they're being virtualized. And then we have the hardware assisted one, such as with Hyper-V, Intel VT and AMD V. Okay, so a key part of understanding code is to really understand machine code and how it actually operates. So in this part of the lecture we'll have a look at some example codes for the x86 architecture. Okay, so the first thing that we need to do is to really understand what's called the von Neumann architecture. So von Neumann came up with this architecture where data and code shared the same space. So we basically had a whole lot of memory, and then we segmented it up into data areas and then code areas. So at one time this used to cause a lot of problems in that we could overwrite our data area with the code and vice versa. But these days these two areas are well isolated. Typically about 4 gigabytes of memory is reserved for each space, and they are isolated. Okay, so we have our microprocessor, and the microprocessor links to some memory, As we've seen, it could be local cache memory, or it could be the large RAM memory on the machine. When the microprocessor wants some data, it puts the address on the address bus, and then controls this, either read-write in terms of a control bus, and then the data will appear here. So if it's writing to memory, it will send the address bus, put some data here on the data bus, and then say write. So it would write into memory. Vice versa, if it's reading from memory, it will put the address on the address bus that it wants to read from. That should then appear on the data bus, and then it would say read, and that way the data would be read into the microprocessor. So the microprocessor really is the brains of the whole of the machine, and most of the things that go on with inside the computer will go through the microprocessor. So we have an area of code that will run, and the current place in the code that we actually are in the memory is defined by this instruction pointer here. We call it EIP because it used to be an instruction pointer which was 16 bits. So as the processor got larger towards 32-bit processors and 64, we increased the amount of space that we can actually access. So it's now an extended instruction pointer, so it can point to a larger area of memory. So wherever we are, we will start in a certain place. We might go through the code. We might have a jump point in the code that will take us somewhere else, execute some more code, and then we might return back to where we were and then continue on with the code. So it's not just sequential code that we actually look at. Often the code will be jumping, looking at it, will be deciding on whether it should branch and so on. So the instruction pointer is holding our place in memory where the next code element actually is. We also have a number of scratchpad type registers, general purpose type registers. This allows us to put something into the microprocessor, do some operations, and then we typically then save it into data. So four more general purpose registers are AX, BX, CX and DX. AX is the most general of all these registers. A lot of the operations that we'll do will typically go through the AX register. We can also have a source and a destination index value that we want to identify when we're writing to memory. An important concept inside a computer's design is what's called the stack pointer. So in data, what we typically have is a heap type memory. We declare a lot of memory and then we just keep adding to it onto a heap. So it can grow and then it can reduce and so on. It's very difficult for us to know how much memory that we've actually allocated, where we are and so on. The concept that we use typically is called the stack, and a stack is a last in first out type principle. What we will do, and it's typically when we're branching, we will put a whole lot of things onto the stack so that when we return we'll pop them back off again so that we know that we're back as we were. So let's say that we were running a program and we had all our registers set up, and then we had to go off to a sub-function, but we wanted, when it came back from the sub-function, for it all to be restored again. The stack is a useful place for that to actually happen, because we can pop our data on and then we can pop it back off. Okay, so in this case the stack grows that way. Data 1 goes in, data 2 goes in, and in this case data 3 goes in. And then, so this is called a push. So we push it onto the stack and then we pop the data off. Okay, this is a pop operation. So when we say push, the data goes in and increases the stack, and then the pop will take the last value that was actually put into the stack and take it out. In this way that we can actually put a temporary data into it and then pop the data out again. Okay, so what does our code actually look like? Well, obviously there's the actual machine code and assembly code. This is just showing the C code in this case. This is showing the disassembled code. We can see the stack here. So this will allow us to see all the values that have been put onto the stack. We can have a look at the registers. So we can see here, there's the registers that we identified before. The red value will actually show us which register has been changed in the last operation. And we can obviously have a look at the memory inside the machine. So in this case we can see hexadecimal. Here's the memory pointer. And there's what it looks like in an ASCII type format. Okay, so those are our main viewpoints when we're looking at code. If it's malicious code, then often we'll actually be stepping through it one line at a time and watching what's happening to the memory, looking at what's happened to the code, what's going on to the stack, and then what's happening inside the registers. And we obviously can see our code here if we have it. Sometimes when we're running with the process itself and only with the machine code, and we don't actually have the original C code. Okay, so this shows an example. So there's our code area and there's our data area. There's our registers inside our processor. So we have an accumulator register, base register, counter, data register. These are all typically used for more specialized functions. Source index, destination index, a base pointer, and then our stack pointer again. So if we take an example of some C code, so it's a very simple example. What we're going to do is have two variables, A and B, and another one called Z. And we're going to add A and B, and we're going to print it out to the screen. So this is the associated code that we have, purely to really start the whole thing going, get the variables in from the actual command line. This is what that's doing there. And then this is actually showing us the code that's associated with each line. So B equals 2 is this code here, and so on. So the code associated with Z is equal to A plus B is here. So we can see there's the push, moves something from a place into a register, and so on. So there's the push and so on. So the code that's actually run on the machine is actually this code here. So the code, the processor doesn't run the original source code. It needs to be compiled in some way. Okay, so if we quickly look at this, what we can actually see is the value of 1 is going into the place in memory of A. This is defining a pointer. It's a data word. It's just 32 bits as an integer. So wherever A is stored, then the value of 1 will be put there. It's quick memory rather than loading it up into the register. If we can get direct memory access, then A can be loaded up with the value of 1. This is loading up the value of 2 for B. And then what we do is that we then can move the value of A into the AX register here. Okay, so AX will be 1 here. That will load the value of B and add it to the current value of EX. So the way to interpret this one is that is equal to EX is equal to EX plus this value here. So that's what the add operation does. And then what we'll do is we'll move the value that's in the AX register into the place where Z is in memory. Okay, so that's the three main, well, the five main operations there that allow us to add two numbers together and put it back into a certain location. So we'll just have a look at that in terms of the code. Okay, so here's our pre-prepared example. Okay, A is equal to 1, B is equal to 2. We'll add the two numbers together and then hopefully we'll get the result. So what we'll do is we'll step through the program. So we typically put the debugger on, and then we'll have a look at all the registers and things and see how that actually goes. So we'll just add in a window here, and so we'll just view. Okay, so that should just break. It should just break, so it's just going to compile it. So that will break when it gets to setting A equal to 1. It's a little console application. Just minimize that. Okay, so we can look at our memory if we want. We can look at any watch points if we have the original source code. You can see it's not set to a value yet, so we can't actually see it. We can't see it hasn't changed from its initial value. So what we'll do is we'll have a look at the disassembly. This should show us our machine code. And then what we'll also have a look at is our registers. Okay, so they're all pre-prepared with something. You can see something has went on before and got everything set up. So what we should find now is that we'll just execute that. Right. Okay, so we can see the instruction pointer has actually changed here. So we can see there is the place in memory. So it's telling it where it should go to find the next piece of code. So in this case there's no branches involved. So we'll just step again. And we can see there that now it's now pointing to the next place in memory. So for the next part we'll see the value of A going into AX. And there it goes, so the value of 1 is in there now. We can see it's taken the value from memory of B and put it into EX, and then it's added it, so we get a value of 3. Now what we're going to do is we're going to then store that to where Z is, and there we go. So we should be able to look at our memory, and then we should be able to find out where actually it's actually stored it. The ampersand gives us a memory location, so that gives us a pointer, so it points to the actual place that it is in memory, and then we should be able to find out where Z actually is. So to 5FBE4. Okay, so there's where it lives there, and there we go, there's the value of 3. So if we wanted to look at the where A is stored, probably A is stored somewhere quite near it. To 5 FBFC. There we go. So we have the value of 1 there, and we can also do the same for B and so on. We can look at our code to see where our code actually is. And in this case, it's at F31A95. Okay, so this is what our code actually looks like in the memory. You can see that it's there in this area here. That's our whole program. That's what the program actually looks like, with all the registers and so on. Okay, so you can see that the code and the data are sharing the same memory space. Okay, so some of the assembly language commands that we see are move. So it moves something from there into there. So it moves it either from a register into another register, or from a memory location into the register, and vice versa. Interrupt allows us to interrupt the processor and do something, such as call up a disk write or something like that. Add and subtract will take the register and then add a value to it or subtract it. We've seen push and pop, so there's the push examples there. Call allows us to call a subroutine, so we can see we're calling a standard subroutine there. Hopefully when it's finished it will come back, it will return to this value here. Compare two values, jump if equal, jump if not equal to, and then a non-conditional jump. Okay, so there's what we have just seen. There's the registers at this point. We then load up the value of 1 into the memory location of A. We change the instruction pointer, it moves on. Load up 2, it changes the instruction pointer to the next place. Then we load up into AX the value of A, or the contents of A. Then we add on the value of B into the AX register, and then we take that and then we load it into the place of Z. So let's see how a function actually works. So in this case we've added a little function called add, and what it'll do is it'll call that function up, add the two numbers together, and then return back the total of them, and then print that out. Okay, so it's much the same as before. Load up with 1 and 2. Then what we do is that we take our values and then we pop them onto the stack. So that's going to preserve our values in some way. So we push it there, we push B onto it, so B is on there, and then A is pushed onto the stack. And then when we return back, they'll be popped off the stack and we'll have them back in memory again. So now what we're going to do is that we're going to actually call up our code. We're going to call up our function. So in this case we're going to call the sub-function called add, and it's going to go to this memory location. So if I actually go to that location, so when the program executes, it will go there, and then we will execute this code. So it's away in another place of memory. So we do our push functions to make sure that the base pointer, so we're going to pop that back off at the end to make sure our base pointer returns back to the right place. We push some other things, such as this one, and hopefully they will all go back preserved, so when we return to the code all our registers will be the same as they were. Okay, so you see lots of push and then pops there. That just allows us to return back to where we actually are. So you can see that the stack can cause lots of problems if it doesn't quite go right, if we don't quite synchronize it. Okay, so this is just the same as before. So we're just adding the two numbers together here, and then we just return the values back through the stack. So you can see there C and D being loaded up and then added into there. So before we finish this, let's look at another type of code, and that's the emulator. So with emulator we have a program which will translate a certain type of machine code and a certain type of architecture directly into a certain hardware architecture. So a good example of this is with the games emulator, such as the ZX Spectrum emulator that we can get to run within Windows. We can also get Dynamips, which will virtualize a Cisco device. Okay, so this is running Dynamips, and we can set up, so it will convert the Cisco code into the native code for a PC. We can also get emulators for mobile devices such as iPhones, Windows Mobile, and so on. So we're going to focus on Microsoft.NET and then on Java to show the problems that occur with inside these types of framework infrastructures. So we'll do a quick recap on what .NET actually is, and then we'll have a look at an example of how we can compile it and then reverse engineer it, and hopefully we can look at the methods that we can use to obfuscate the code. So basically, as we said, the .NET framework integrates lots of things like Web, Com+, which is for highly optimized systems, large-scale systems, such as database infrastructures, and we have our normal API type interfaces that we can call within our side of code. That produces our executable program, an exe, which is intermediate code, using typically C# or VB.NET within a Visual Studio environment. Lots of advantages. We have a common runtime language, which is fairly standard across all the .NET programs. We have a common framework class library, which makes sure that all our objects are the same, that have the same type, same specification, such as the same properties, methods, and so on. We have a common type language where we have standard definitions for integers, floats, and so on. And also we have a common language specification which allows .NET to be built through most types of languages: C#, VB.NET, G#, Fortran, Delphi, and so on. And the framework itself is contained on the system in a number of different versions. So this one here is version 1.1, 4.3.2.2 release, and it basically has all the DLLs that are required inside the framework. So these are carefully managed to make sure that they can actually be modified. So when a program needs access to, say, a file I/O, it will call in the MS Core lib DLL and get access to the code that it requires for that. So if we have a little look at this, so we should find that it is actually stored on the system. So you can see here we have version 1.0, 1.1, 2.0 and so on. If we go in, then we should be able to see our core libraries and so on. So there's the MS Core lib for .NET 2. So a program runs in a certain version and it will use the framework that it was bound to. So what happens is that we take an intermediate code, and many applications can run, and they should all be isolated from each other and uncrashable. Then they run within there. We still have a native code that runs on the system. It's this code that could cause damage to the system and cause the system to crash. If everything was on the .NET framework, then the system wouldn't actually crash. So the framework really converts from this intermediate format into the native code for the operating system. And we've went through various versions from 1.0 up to 1.1. 2.0 was a major breakthrough with ASP.NET, 64-bit support and Bluetooth. Then we got the three main packages that have been developed further. We have the Presentation Foundation, which is next generation graphics, Communication Foundation, which allows for client-server type contracts to be created, which binds connections together over a network as if they were local. And then we have Workflow, which allows us to define workers and threads and so on that could work on other machines. From here, we've developed onto .NET 4, which has parallel task support, parallel link and background garbage collection, and the latest one that's been released is 4.5. Okay, so we've looked at .NET, and let's have a look at the code that produces. So we have our C# program for .NET. That is then compiled into an intermediate format. So we can see our intermediate format here. Looks roughly the same as it stores all the variable names and the string names and so on. So we can actually pick up all our class names, names of variables, types, and so on, and all the methods that are used. So what we do is we will take an example where we'll take the CS file, we then compile it to an exe, then we'll run it, and then we'll see if we can reverse engineer the code back again, because it's important that we protect the code, so we'll have to use obfuscation on it. Okay, so let's try. Okay, so let's delete the exe and we're just left with the CS file. So what we'll do is we'll compile the C# code, and that should have created an exe for us. Okay, so here is our code. Now what we'll do is that we'll see if we can get the code back again. Okay, so we'll just run the code just to see if it's working. Okay, so what we'll do is we'll run exemplar, which is allows us to reverse engineer the program. Now you can see here it's reproduced exactly the code back again. Okay, so that's what we did. We used exemplar from our exe, and that was able to get the C code, the C# code back again. And we can see here the code itself is almost exactly the same. So we can use many packages such as .NET Reflector to be able to examine the actual code itself, the assembly as it's called, and to look at all the basic types and the code itself, purely from the exe. Okay, so it's possible to also do the same with Java. So we can have a package called Jade which can decompile our code. So we'll take an example here. Okay, so we have our Java code. Then what we'll do is we'll compile it into our bytecode. It takes a little bit longer than the C# compiler, but it should get them. It's a very simple code. Okay, so there's our class file. Just check. Very simple program here. Now we can run JAD on our class file. We see it's created our JAD file. And we can see here we have the code exactly back. So anything that runs with inside a framework is likely to be fairly easy to reverse engineer. Okay, so there we are. There's our Java file. We compile it, we get a class file. We then can run the program if we want it with the Java runtime environment. We then use JAD to be able to read the class file, which creates our JAD file, which gives us back the original code. So now that we can see the weakness of the basic process of .NET and Java, let's look at how we can obfuscate our code to make sure that it can't be reversed, or at least this original source code can't be recovered. So this is an example of what's called obfuscation. This is actually a real C program, and it is possible to run this, but it's very difficult to tell what it is. And basically, if you were to run it, what you would get is the 12 Days of Christmas. And what they've done is they've eliminated white space, which we like because it makes it easier for us to read. Our eyes are drawn towards white space. It uses conditional and list expressions instead of the more familiar if-then else statements and blocks, and it uses simple encoding for strings that we find it difficult to interpret, and it uses multiple functions instead of a single one that we would normally expect. So the methods that are typically used to obfuscate is to take our nice variable names and our nice class names and then to convert them into some other format. In this case they've been integrated, they've been changed into a non-printing format, so it's very difficult for a human to be able to understand and trace these variables. So even though the code could actually be run again, it's very difficult to maintain the code at all. We also get string encryption, where the actual strings themselves are encrypted in a form. So you can see here it's very difficult to see what the string name actually is. It is possible to find out the encryption because the key is actually stored within inside the obfuscated package, but at least stops someone from searching through the program to be able to find the actual strings, the original strings. And then they do some flow obfuscation where they can scramble the code, so it's very difficult to trace what it actually does. Okay, so let's take an example of obfuscation, and we'll go back to our example here. Okay, so we have a simple program. Our simple program. So as we've seen, we can get that back. So what we'll do is that we'll run a basic obfuscator. So in this case we're running .obfuscator. So we can see now that it's actually crashed the program, so we can't actually see what's in it. So the program itself will try to generally crash any reverse engineering package. Okay, so this is an example. So we have our original code. This is the intermediate code. We can then see that there's a very simple obfuscation. The names have been changed, in this case from class 1 to A and from name to V0. So we haven't actually encrypted any of the strings here or hid any of the methods used by the objects, but it shows a very simple example of how we can change the names and the classes. And as we said, what will typically happen is that the reverse engineered package will crash. One thing that we often do when we're analysing code is to look at its footprint on a host, such as looking at CPU utilization, its memory, the files that it opens, and so on. So one thing we often do is we often run a debugger to be able to actually step through our program to validate it and to make sure that everything is working properly and to optimize it. And we often bring up the debugger so we can hook on the process. We can hook on a running process on the system with inside Visual Studio. So we select attach to process if we have a running piece of code, and then we can actually select from one of the programs that are actually run on the machine, and from that we can actually debug our code from there. And from here we can see the registers, we can see the actual intermediate code or the machine code and the actual code running itself. We can also go for a dynamic analysis, so in this case we're looking at the performance monitor on the machine, but any of these metrics can be gathered through our .NET counters. And then we might look at some file trace to see the types of files that our program is opening and how it touches the registry and the threads that are created. So for example, we might use a program such as this to be able to look. In this case we could look at the trace of the registry. So we just have to filter. So this is for a specific program or process name that's actually run. So this shows all the keys that were opened and wrote to within that program, and you can see that even a program just starting up is opening and closing, interrogating lots of files from the registry. So that's within just a few seconds. It's accessing the registry many hundreds of times. So that's just 1 minute. These are all the accesses to our registry. So that's why you can see if the registry is corrupt, then the whole machine is often corrupt. We can look at the files which are opened from it. So we would typically start our process monitor up when the program has been run, and then it will capture all the events. Just to disable that one. And this shows the actual graphics that are being loaded and the content that are loaded with inside the system. So this gives us the basic footprint, and we can get other tools such as registry compare tools, where we can look at the registry before a program starts and after it, and actually look at the differences in the registries between the two. We can also get programs which will determine the files which have been opened and so on. So how do we really validate that something has been changed? Well, often what we do is that we take hash signature such as MD5. So in this case we've taken a few hash signatures of files, and then we can see that none of these files have been changed until we get to this one here. I can see here that the hash signature of that file has actually been changed, so that there's been some modification on the file. All the other ones are still the same. Okay, so we have a basic file trace, and we can have our registry audit too. Then when we're debugging a program, we can look at its memory, we look at its disassembled code, we look at the stack, and so on, and we can actually step through the program one line at a time and try and understand its operation and hopefully its footprint on the system. This way we can identify bottlenecks or even malicious code.